Imagine you have a machine, a black box. You can feed it a picture of dog and it outputs the word dog. You can feed it the first half of a sentence and it writes the second half. You can feed it the sensor data from the car's radar and it outputs the command turn left. But it feels like magic. Or maybe it feels like an infinite if-else statements written by 1,000 engineers. But it's not. The modern miracle of artificial intelligence rests on a single, surprisingly simple mathematical guarantee. A guarantee that says, strictly speaking, you don't need a complex brain to solve complex problems. You just need enough simple neurons arranged in a single linear layer to approximate any pattern in the universe. This is the Universal Approximation Theorem. It is the mathematical proof that a neural network aren't just lucky guessers. They are universal function approximators. In this episode, we are going to prove visually right here why deep learning actually works. By the end of this video, you won't just trust the black box. You'll understand the gears inside it. Hey everyone, welcome back to Sumantra Codes. I'm Sumantra. I remember when I first started learning AI, I was told just stack more layers. It will figure it out. But that answer never satisfied me. Why does stacking numbers in a matrix allow a computer to understand human speech? In 1989, a mathematician named George Cybenko proved something incredible for sigmoid activation function. Later, Hornik expanded this in 1991 to practically all activation functions. They proved that a feed-forward network with a single hidden layer containing a finite number of neurons can approximate a continuous functions on a compact subset of real number. Okay, translation please. It means that if you have a problem that can be described as a continuous line on a graph, a neural network can learn to draw that line. It doesn't matter how wiggly, how complex, or how weird that line is. If you give the network enough neurons, it can copy that line with as much precision as you want. This theorem is just a bedrock of confidence of every AI researcher. It tells us that the solution exists. We have to find it. So grab your notepad, let's do some math. To understand the theorem, we have to start with philosophical shift. You need to stop seeing the world as objects and start seeing the world as functions. In computer science, a function is a machine. It takes an input, processes it, and it spits out an output. Y is equal to fx. Let's look at a simple example. House prices. Input x is the square footage of the house. Output y is the price in dollar. If we plot from 1,000 houses, we might see a pattern. It goes up, maybe it curves a bit, because eventually a house is so big that nobody wants to buy it. So the price per square foot drops. The curve, that's a function. Now let's get more abstract. What is a grayscale image? It's a grid of pixel values, right? Let's say we have a tiny 28 by 28 image of a handwritten number. That's 784 pixels. We can just treat those 784 pixels as 784 inputs, x1, x2 to x784. The output y is the digit 0, 1, 2 up to 9. There exists some complex, squiggly, multidimensional mathematical function that maps those pixel intensity values to the correct number. We don't know the equation. It's not y is equal to mx plus b. It's probably y equal to 3x1 square plus sine x2 minus log x3 ... for million of pages. But it's a function. The Universal Approximation Theorem has one major condition. The function must be continuous. Continuous means you can draw it without lifting your pen. Real life is mostly continuous. If I move my steering wheel 1 degree to the left, the car moves slightly to the left. It doesn't teleport to Mars because the physics of our universe are mostly continuous. We can use neural networks to model them. So we are trying to build a universal function approximator, the machine that can look at a squiggly line on this board and mold itself to match that shape perfectly. How do we build this machine? We start with the atom of deep learning, the neuron. You might have seen diagrams of neurons connected with lines, but what is it mathematically? A equal to sigmoid of dot product of weight into x plus bias. Let's break this down. This simple equation has two distinct steps. First, the linear transformation, wx plus p. This part is just a straight line. W or weight, this controls the steepness or slope of the line. Bias or b, this controls the position. It shifts the line left or right. If we stop here, we would have a linear regression, and linear regression perform poorly at complex problems. If I tried to predict the stock market with straight line, I'd be broke. We need curvature. We need nonlinearity. Step 2, the activation function sigma. We take the result of that straight line and pass it through a squashing function. Historically, we use sigmoid function. Look at the shape. It's an S-curve. For very negative numbers, it's close to 0. For very positive number, it's close to 1. In the middle, it transitions smoothly. Now, watch what happens if we mess with the weight inside this sigmoid. If we make W really big, like 100 or 1000, what happened to the slope in the middle? It gets steeper and steeper until it becomes a step function. It looks like a cliff. Everything to the left of the bias is 0. Everything to the right of the bias is 1. This is the aha moment. The single neuron with the high weight acts like a switch. It says, is the input X greater than the bias? If yes, turn on. If no, turn off. So we have a tool that can create a step, a cliff. But most functions aren't just one single cliff. They are mountains and valleys. How do we make a mountain out of cliffs? This is where the magic happens. This is where we combine neuron to create something new. The theorem focuses on the hidden layer. Let's imagine a network with one input X, one hidden layer with two neurons, one output. Let's call the two neurons neurons A and neuron B. We are going to configure them specifically to build a bump or a tower. Step 1. Configure neuron A. I want A to turn on or jump from 0 to 1 at position X is equal to 2. So I set the bias, so the step is at 2. Step 2. Configure neuron B. Similarly, step 2, I want neuron B to turn on at position X is equal to 3. Okay, so now we have two switches. If X is 1 or less than 2, both represent 0. If X is 2.5 or between 2 and 3, A is 1, B is 0. And if X is 4, that is greater than 3, both are 1. Now we send these signals to the output neuron. The output neuron sums them up, but it multiplies them with their output first. Let's give neuron A a weight of +1. Let's give neuron B a weight of -1. Let's do the math visually. So before X equal to 2, we have 0 minus 0, which is 0, a flat line. Between X equal to 2 and X equal to 3, neuron A is on or 1, neuron B is off or 0. So calculation is 1 minus 0, which is 1. And after X equal to 3, neuron A is on 1, neuron B is on 1, calculation is 1 minus 1 equal to 0. Look at that, we have created a tower. By combining just two neurons in a hidden layer, we created an activation that is localized. It only exists between X equal to 2 and X equal to 3. Everywhere it's silence. And here is the kicker. We can change the height of this tower by changing the output weights. Instead of +1 and -1, if you use -+5 and -5, the tower grows to height 5. We can change the width of the tower by moving the biases of the two neurons closer or further apart. We can slide the tower anywhere along the x-axis. So, a pair of neurons acts like a Lego brick. We can make it tall, short, wide, narrow, and place it anywhere we want. Now, we are ready for the proof. Here's the generic continuous function fx. It represents something complex. Maybe the sound wave of me saying, hello. How does our neural network replicate this? Well, you probably learned this in calculus. Remember Riemann sums? When you wanted to find area under a curve, what did you do? You drew rectangles. We can approximate this complex function by stacking our neural towers side by side. For the first section of curve, we configure a pair of neurons to build a tower that matches the average height of the curve at that spot. For the next section, we use another pair of neurons to build tower for the next height. We keep doing this all the way across the domain. This is an approximation. It's not perfect, it's look blocky. The Universal Approximation Theorem speaks of arbitrary accuracy. That means we can get as close as to the real curve as we want. The error epsilon can be as tiny as you desire. How do we reduce error? We make blocks thinner. If we make the blocks half as wide, we can capture the wiggles better. But if we make the blocks narrower, we need more of them to cover the whole graph. And remember, every block required two neurons. If we let the width of these towers approaches 0, the number of towers approaches infinity. The jagged steps smooth out. Our approximation becomes indistinguishable from the target function. So, what we have proven? We proved that a sum of step functions can build any shape. And since neurons are step functions, basically, a sum of neurons can build any shape. This means a neural network is not thinking in the biological sense. It is constructing a highly complex, multidimensional mosaic of towers to mimic the data you fed it. I know what you're thinking. Sumantra, if one hidden layer can do anything, why do we have deep learning? Why do we have networks with 100 layers like ResNet or GPT-4? That's an excellent question. The theorem says a single layer is sufficient, but it doesn't say it's efficient. To approximate a really complex function like distinguishing distinguishing a cat from a dog in a 4K image with just one layer, you would need an astronomically large number of neurons. We are talking about billions or trillions of neurons in that one wide layer. It would be impossible to store in memory, impossible to train, it would overfit instantly. This is where deep learning enters the chat. When we stack layers on top of each other, we aren't just adding more bumps. We are creating compositionality. Layer 1 finds edges or simple lines. Layer 2 combines edges to make shapes like corners, circles. Then layer 3 combines shape to make textures or objects parts, such as eyes or wheel. And finally, layer 4 combines parts to identify objects. By stacking layers, we can approximate the same function with exponentially fewer neurons. The Universal Approximation Theorem tells us that it is possible to solve the problem. Deep learning tells us how to do it efficiently. But never forget, the foundation is that first layer, the fact that the mathematical sum of nonlinear units can represent any reality. So let's recap the journey we took. The world is functions. Whether it's stock prices or language, everything is mapping from input to output. Neurons are switches. A neuron with a bias and a weight acts like a soft step function. Two neurons make a bump. By subtracting two offset neurons, we created a localized tower of activation. Towers build shape. By stacking enough of these towers side by side, we can approximate any continuous curve to arbitrary accuracy. This theorem removes the mystique of AI. It's not magic, it's approximation. It's the brute force elegance of the mathematics. Next time you see a neural network do something incredible, visualize those billions of tiny towers rising and falling, shifting and scaling, trying to match the curve of reality. I have a challenge for you. In the comments below, I want you to tell me what is a function in your daily life you wish you could approximate. Is it a function of how much coffee leads to maximum productivity? Or is it what text message makes my friend reply faster? Let me know. If you enjoyed this Blackboard style deep dive, hit that like button. It helps the YouTube algorithm approximate my channel to more engineers like you. And if you haven't already subscribed to Sumantra Code, please do that. Thanks for watching and keep coding.